Okay, so our goal really is to solve systems of differential equations, and eigenvalues and eigenvectors and actually diagonalizing matrices is going to be the key to this. Actually, I suppose what I want to say is that if you have a system with lots of variables, lots of degrees of freedom, either mechanical positions or electrical parameters, if that system's highly coupled so that everything's related to everything else, then you get a matrix that's not diagonal. And somehow the idea of diagonalizing a matrix is changing variables so that they're uncoupled. And uncoupled is kind of an engineering word for diagonalize. So any big system of differential equations, whether it's to do with vibrating buildings in earthquakes, understanding the vibrations in the building due to wind, or the differential equation of brake squealing, or of course any large electronic circuit that has oscillators in, then diagonalizing decouples it, a big system of differential equations relating everything to everything else into something like separate modes that you can treat independently. Okay, so that's kind of a sneak preview. We've done the case where we've got all the eigenvalues we need, but not all matrices are that nice. They're not all normal, in that rather strange word. So the difficult case is where the eigenvalues are repeated, but there's not enough eigenvectors to make n independent eigenvectors, and we've seen that that's possible in a very simple case. In that case, diagonalization goes wrong. So here's a matrix that we met, the 2, 2 on the diagonal, so the eigenvalues are 2, just repeated, but there was only one independent eigenvector, so we can't diagonalize that. There's the eigenvalues, and there's our one eigenvector. Actually, there is a sense in which the best you can do in that situation is get down to, well, in general, ones that are just off the diagonal where the same numbers are repeated. So even if it's a huge matrix, the eigenvalues are repeated. Actually, this is archetypal because the worst that you can get, once you've tried to diagonalize it, is these irritating ones off the diagonal. So we can't do this because we've only got one independent eigenvector. We can write it twice with different multiple, but look, this matrix is singular, and so we can't use it to diagonalize. Let's try another diagonalization. Here's a matrix. Doesn't look singular, does it? Let's see. Well, the eigenvalues we can work out are -3, 1 and 1. We do that by solving the characteristic equation. And then once we solve the characteristic equation and find the eigenvalues, we get the matrix A and subtract each of the eigenvalues from diagonal in turn. And then we solve the system with Gaussian elimination, or just spotting it sometimes if it's easy. And then we get the eigenvectors. So in this case, actually, of course, we'll only get one unknown parameter because there can only be one eigenvector, because you can't have more than 3 independent vectors in 3 dimensions, can you? So what comes out of Gaussian elimination is, say, for example, t over 3, t over 3, depending on how we choose the unknown parameter t, which can be written as t as a function of t, but say if we take 3, t is 3, we get a neat solution 1, 3, 1, I mean, just to make the numbers nice. For eigenvalue 1, actually just check the eigenvalues were, this was actually repeated, wasn't it? So we might get into trouble here. Oh, it's got repeated eigenvalue, so it may or may not work. Let's take the eigenvalue for lambda equals 1. Actually, going back to the matrix, we might be able to spot that. It says if we subtract 1 from the diagonal, let's just see what happens there. Look, we get 4 there, 12 there, and 4 there. You see what's happened? Look at the columns. The columns are actually just multiples of each other. So there's kind of only one independent column. And similarly, there's only one independent row for this. So what happens for lambda equals 1 is when we solve it, the eigenvector, the solution depends on two parameters, s and t, and the general solution is s, t minus 1. And so we can take different values of s and t, and I just choose convenient ones, 1 and 0 and 0 and 1. You can take any two values, but of course choosing them as 1 and 0 just makes for neat arithmetic. So examples of two of the vectors in this set of solutions are 1, 0, minus 1 and 0, 1, 1. Any combination of those will still be an eigenvector for the eigenvalue 1, but the point is we've got two independent ones. Clearly these are not multiples of each other, so they're independent eigenvectors. So we've got independent eigenvectors. If the matrix was symmetric, we could say that they're orthogonal. The original matrix wasn't symmetric, so we've no right to expect that particularly. So we write down the matrix P. There's the eigenvector for 1, and there are two of the eigenvectors for lambda equals 1, and they are independent because these are clearly independent of each other, and because these are for different eigenvalues, this must be independent of those two. So it turns out the matrix is invertible. It looks like maybe the determinant's 1. Not sure. But we can invert it. So we work out the inverse using the formula, if you like. In any case, you can check that this is in the inverse, and D is the diagonal minus 3, 1, 1. So that has been able to diagonalize it, and the trick was, even though it had repeated roots, it had two different eigenvalues.